Okay, so we're back. This is week 11, video number 2. The first video we just concluded talking about the hydrocarbons, alkanes, alkenes, alkynes, aromatic compounds, and we saw 3 different types of reactions that alkenes and alkynes undergo, right? We also learned that aromatic compounds were very unreactive. Now, that was chapter 11 stuff in your book. So this is going to be chapter 12 we're starting now. And that's when we have organic compounds with oxygen, sulfur, or a halogen. I want to tell you, if I had a pen right now, I'd put a box around the O and cross out the S and the halogen. This is mainly all about organic compounds with oxygen. Okay? So the first compound with oxygen that I can think of, and I think that's important, is alcohols. Alcohols have something called a hydroxyl group. Hydroxyl group is just an OH, single bonded to a saturated carbon. Saturated carbon is a carbon that makes 4 bonds. All right? So example, CH3OH, methanol. CH3CH2OH, ethanol. Very similar to methane and ethane, but we have an OH group on them. All right? Now the next example is very common, so you need to know it. And I've drawn it out for you because the formula looks a little funny. That's isopropyl alcohol, and that is CH32 CHOH. All right, basically the OH is attached to a carbon that is also attached to 2 other methyl groups. That's an isopropyl group. All right, next example, the 4th one there is glycerol. I'm including it because later on in the course this is important as a backbone for fats when we talk about lipids in the biochem portion of this course. It's just a 3-carbon alkane, but it's got OH, OH, OH on it, so it's no longer an alkane, it's an alcohol. 3 OHs makes it a triol. All right, top of page 2 of our notes, phenols. So it's got the OL ending, kind of like an alcohol, but phenols are not alcohols. Phenols have an OH group bonded directly to an aromatic ring. And in this class, the aromatic ring we know of is benzene. So if I have a benzene ring with OH on it, that is simply called phenol. Please be careful. An OH group attached to an aromatic ring is not an alcohol. This is a phenol. Now, the other one I've drawn next door, see how the OH is not attached directly to the ring? It's attached to the CH2 group. This is not a phenol. This actually is an alcohol. So the one on the left is phenol. The one on the right is an alcohol, which I'm not going to name. Not at this time, anyway. Ethers. All right, ethers, the functional group for an ether is an oxygen atom single bonded to 2 organic carbons. So if I'm the oxygen, I am single bonded to 2 carbons. So you see how, example here, CH3, CH2O, CH2, CH3. If I draw that all out for you, you can see how the oxygen is smack dab in the middle of the carbon-carbon-carbon-carbon sequence. On each side of the oxygen, it's an ethyl group. That's why it's called diethyl ether. Diethyl ether is the common name. We won't see too much about ethers, too much about phenols, mainly alcohols, ketones, aldehydes in this chapter. Alcohols, ketones, aldehydes are the major ones in this chapter. How do we name alcohols? Well, there's 3 steps, and of course we know how to name alkanes and alkenes already, so we kind of have that knowledge behind us. First, you're supposed to name the parent compound. And if it's an alcohol, you darn sure better have the OH in the parent compound. So find the longest chain with OH attached, and then we use the OL ending, all, like alcohol. So let's do an example and then figure out how to name it. All right, the example here, I've got CH3CH2 with a CH3 off of the 2nd carbon in on the left. And so I see the OH has to be in my chain. This is going to be a 6-carbon chain with my OH in it, so it's some sort of hexanol. All right, we will use rule number 2 to move forward with our naming on this. So I see that we have a hexanol. We also have a CH3 branch. Now for rings, it wouldn't be a hexanol, it would be a cyclohexanol. My example in parentheses, if it were a ring, it would be a cyclohexanol. But this is a straight chain. Our main example is a straight chain, so it's some sort of quote-unquote hexanol. We have to properly name it. Number 2, the carbons in the main chain need to be numbered. Start at the end closer to the hydroxyl group. The hydroxyl group gets preference over that CH3 branch that you see sticking up. So my far left carbon is not necessarily carbon 2. In fact, here it's carbon 6 because I want the 3 to be lower for my OH, whereas if I numbered from the left, it would have been carbon 4. So I'm just numbering my carbons here, and I'm going to take my cyclohexanol example along with us here. So I've numbered that with the OH getting the 1. The OH will always get the 1 if it's attached to a ring. Now, that's not a phenol, that's an alcohol, because that's just a plain old ring. That's not an aromatic ring. That's just a plain old ring. Rule number 3, write the name of the alcohol. Okay, so I know I have a 5-methyl group. Put the branch first, and then I write 5-methyl-3-hexanol. Read out loud, that's 5-methyl-3-hexanol. Now let's go to my cyclohexanol. Remember, this is not a benzene ring. That's why this is an alcohol. 2-methyl-cyclohexanol. You don't have to say 2-methyl-1-cyclohexanol. The 1 is understood because the OH will always get the 1 if it's attached to a cyclohexane ring like that, cyclohexanol. Some other alcohol examples. CH3, CH2, CH2, CH2OH. That's just 4 carbons with an OH on it. B, we have a OH off of the second carbon. So this first one is just simply 1-butanol. I have to call it 1-butanol because I have to specify the OH is on carbon 1. For B, I have 2 OHs. Okay, so this is 1,2-propane-diol. Be very careful on the naming of this. Instinctively, almost every student I've ever taught wants to call this 1,2-dipropanol. Do not make this mistake. It's not 1,2-dipropanol. It's 1,2-propane-diol. Very careful. C, CH3, CH, CH2, CH, CH2, CH, CH3 with OH, Cl, CH3. I know the OH has to be involved in the main chain, and this is going to be obviously numbered from the left is carbon 1, the far end is carbon 7. This is 4-chloro, 6-methyl, 2-heptanol. The chloro comes first, then the methyl, ABC order. It's not 4 before 6. It's not numerical order, it's ABC order. All right, so just like the alkyl groups that we learned about in week 10. In week 10, we learned about primary, secondary, tertiary carbons. So just like the alkyl groups, alcohols are also classified as primary, secondary, tertiary. First example I'm drawing, this is a primary alcohol because the carbon that the OH is attached to one other carbon. These R groups that I'm circling are carbon, they're just carbon chains. Okay? The secondary alcohol, the carbon that the OH is attached to 2 other R's. Tertiary alcohol, the carbon that the OH is attached to is itself attached to 3 other carbons. So why am I writing R instead of carbon? Because it's a carbon compound. It could be a CH3, it could be an ethyl, a propyl, isopropyl, anything like that. That's all carbon based. All right, let's talk about some properties of alcohols. Alcohols have an OH group, and if you break down what an OH group is, it's a CO bond, right? Plus an OH bond. Well, these have polarity. Remember when we talked about electronegativity? We talked about the tug of war and how oxygen is more electron withdrawing and is going to tug electrons towards it. That creates polarity, which also, because if it creates polarity and it's polar, it's going to be more soluble in water, right? Whereas alkanes are all CC single bonds and CH single bonds. They're not soluble in water to any great extent. So alcohols, at the very top, it says much more polar than hydrocarbons because of the electronegative oxygen atom. And I've drawn out, what's the example I've drawn here? Ethanol. You see the carbon-oxygen bond has a dipole moment. The oxygen-hydrogen bond has a dipole moment. So we have a polarity in the direction of the oxygen. Okay, that makes ethanol polar. And if it's polar and water is also polar, the two are going to be miscible. Ethanol, which is drinking alcohol, is clearly soluble in water. Most people know that. Now, in ethanol, I have a small organic or alkane part. So it's small enough that ethanol remains soluble in water. But if I have something large at the bottom of my page here, like 1-heptanol, look how large that non-polar organic part is. Look at all those carbon hydrogens and carbon-carbon bonds. This is not going to be soluble in water. Yes, we have a polar group at the very end, but that giant nonpolar part dominates the 1-heptanol molecule. All right. So next page of notes here, I got a double line, which means I'm kind of moving on to something else. And it says the OH group, right, the hydroxyl group, allows for something called hydrogen bonding. Hydrogen bonding is actually an intermolecular force. It's a force between molecules. So if you want to boil something, right, here's two molecules. If you want to boil something, you have to get rid of that intermolecular force so that they can boil off as vapors. The OH group allows for something called hydrogen bonding. It's an intermolecular force between molecules. So alcohols have relatively high boiling points. Well, a high boiling point means you have a very good attraction for molecules within one another. All right. So, for example, 1-butanol, boiling point 117. 1,4-butane-diol, boiling point 230. Notice that's not 1,4-dibutanol. Careful. So let's do an example. Which one has the highest boiling point? A, CH3, CH2, CH2OH, or do I want to choose CH3, CH2O, CH3, or C? So I have an alcohol with 3 carbons, I have an ether with 3 carbons, and I have a 3-carbon alkane. So alcohol is going to have the higher boiling point because it has a polar OH group. That ether has 2 polar bonds, but it's almost like two horses opposing each other. Those electronegativities are going to cancel. And then alkanes we know are nonpolar. So the answer would be the alcohol. Next example. Which of the following is most soluble in water? In other words, which one is the most polar? Okay? Which one is the most polar, or which one is the smallest? Okay? If it has a big, long carbon, hydrogen stuff, we don't want it. So A, look at A. A has 12. A has got 12 carbons in a string with all the C, C's, and CH's. We're not going to like that. Now, C is an ether, 3-carbon ether. B is a 4-carbon alcohol. So when in doubt, you want to choose the alcohol, which I've done for B. Hey, A is also an alcohol, though. Yes, but look at the 12 carbons it has. Those 12 carbons are this. Look, C, 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 all single bonded. Those are nonpolar bonds. And then all the CH's around it. CH is essentially a nonpolar bond too. So I'm writing here with a sad face, huge organic nonpolar part makes that alcohol with the polar functional group, the OH group, not soluble in water. All right, last part of today's notes is actually, in my opinion, the most important part to know, and that is reactions of alcohols. This video will have dehydration in it, and then the next video we're going to continue with our reactions of alcohols. So for this week, video 2 is going to end here with reactions of alcohols. Dehydration, just how it sounds, removal of water. So see the H and the OH in the alcohol? You got to be on a next door carbon. All right, if you add H plus in heat, we can remove that and make a double bond. And then what's our side product? If it's dehydration, our byproduct or our side product is H2O. So let's practice some of those. Example, what alkenes might be formed by dehydration of the following alcohols? When you dehydrate an alcohol, what do you get? You get an alkene. All right, so we want to indicate the major product as well. If you ever make an alkene product, the one that has the most organic parts attached to it is the most favorable. So here I have what? That is 1-propanol. And for B, I have cyclohexanol. So I'm going to draw out A, CH3, CH, CH2. I'm just drawing out the specific H that I'm going to remove and the OH, just so you can kind of see what the product is going to be a little bit better. And then I've done so right there. Okay. So there's my one product. Notice how the OH and the H have to be next door to each other. So for this next one, OH, if I dehydrate this with H plus and heat as my reagents, I get the double bond. Now you might think you get two different products, right? Because you got H's on, if you have an OH, I got the H above and the H below the OH on my ring. But really, it's the same product. I could just kind of flip them like that, right? Swivel it. All right, C. Again, we're trying to choose what the product would be of a dehydration reaction. So I got my OH right there off of carbon 2. I'm going to blow this out and redraw it so I can see the hydrogens that we're going to remove. And we have 2 potential hydrogens that we can remove. Okay, we got the hydrogen to the left of the OH on the next door carbon and the OH to the right. And I've kind of highlighted those with a little circle. So if I remove the hydrogen on the left, which is off of carbon 1, I get what's known as a terminal alkene. A terminal alkene is when the double bond is on the far end of the molecule. And for the product on the right, using H plus and heat to make a dehydration, this is called an internal alkene. An internal alkene is when the double bond is kind of in the interior of the molecule. And if it's in the interior of the molecule, the internal alkene has got more branches off of the double bond, and that makes it more favorable than a terminal alkene. Okay? Terminal alkene, the far left carbon or far right carbon, but in this case the far left carbon only has 2 H's, and those aren't branches. We want more, the more organic stuff, the more R's we see off of an alkene, the better the chances of it being a major product. All right, so that's the dehydration reaction. Next video, we're going to start out with alcohol reactions. We still have some more reactions of alcohols. We have to oxidize them, and that's coming up in video number 3 for this week. All right.